Hi everyone, today I would like to talk about a very important concept, namely the Bayes estimator. I've been talking about Bayesian estimation in the last couple of videos. MMSE, MAP, they are all a special class of a Bayes estimator. So today I would like to tell you what I mean by Bayes estimator. Then I will prove to you that the MMSE and MAP, they are all a special class of this estimator. And also, I will solve one more example about the least absolute error criterion, which is another special class of Bayes estimator. Okay, so let's start. Now, like always, first, let's remind ourselves what Bayesian estimation. This is our first video in this essential estimation techniques series. I will put a link in the description for you to check the first video, Bayesian versus Frequentists. During the Bayesian estimation, we talked about the fact that Bayesian estimation, they assume the parameter theta is a random variable. Is a random variable with unknown distribution. Unknown distribution. Good. Now, this is about the concept that we need for this video for Bayes estimator. Now, during the Bayes estimator, there is a concept that, or there is a term that we need to define. Usually is shown by C or sometimes with L, right? It's C of theta hat. C is cost, or for L is a loss, right? It's a cost of choosing theta hat instead of theta, right? So this theta hat is our estimator. So you can think of it as a penalty. How much we lose if we choose the estimator instead of our actual parameter, our true parameter. How much we should get, how much we should penalize if we choose a theta hat instead of theta, right? Or in the case of you use L, is how much you lose exactly, the loss function, right? The cost of choosing theta hat instead of theta, okay? So during the Bayes estimator, you are going to minimize, I will write the goal first, but this is the goal. So first, it's important to understand the goal. What's the objective in a Bayes estimator? You are trying to minimize the expected value of this cost function, right? After you observe data. This is data. So the goal in a Bayes estimator, Bayesian estimation, is usually you are trying to minimize some sort of cost function after you observe data. Okay, expected value of this cost function after you observe data. Why expected value? Because this, remember, theta is a random variable, so you need to actually come up with an expectation to have one number at the end. You want to compare different estimator, right? So that's what the expected value is saying. Now you want to observe data. If you don't observe any data, then you have no evidence. You have only your prior belief, right? Which your estimation will not be really accurate. But here, after you observe some data, you want to see what is the best estimator, what is the estimator that minimizes the error in some sense. Because it depends on the cost function that you define. So this will be equal to integral of C of theta hat P of theta given x, right? D theta. Okay, so this is just a definition of conditional expectation. Note again, like always, note expected value of y given x, assume they're continuous, is equal to y f of y given x dy. This is the same thing. This is function of the theta, right? It's gonna be C of theta hat times probability of theta given x, which is x is the one in the right hand side of this condition expression, this condition, this bar operator. Now, this is the cost function. This is posterior distribution. Remember, I said posterior is very important in the context of Bayesian estimation as opposed to likelihood. That's where we use this one. This is a generic concept in the domain of Bayesian estimation and Bayes estimator. Okay, so this is what we are trying to do. We are trying to minimize. That's the goal. We are trying to minimize. Let me just allow some room here. We are trying to minimize this expression. Okay, good. Now, like always, I would like to give you a step-by-step technique to approach Bayes estimator problems. Step one, now that we know what we are trying to do, the goal, step one is choose the appropriate cost function. Appropriate cost function. What do I mean by cost function? I mean C of theta and theta hat. The penalty that you get if you choose theta hat instead of theta. Step two, plug. It's time to name these equations. Just use equation 1. Plug 1 in step 1. Plug step 1. Cost function in equation 1 and simplify the integral of simplified expression. Simplify the expression over there. Simplify the expression. Now step 3, try to minimize this expression part 2. Try to minimize the resulting expression part 2. Resulting expression in part 2. That's step 2. So that's what you are trying to do, right? Try to minimize the expression in a step 2. Okay, so that's the whole idea behind the Bayes estimation. Now I want to look into this cost function. The step-by-step technique requires us to first choose this cost function. This is the most important part, right? So let's go ahead and take a couple of cases. Case 1. The C of theta and theta hat is equal to this expression, quadratic cost. What if we choose a quadratic cost? Let's go ahead and find the estimator in this sense. Right? Again, let's call it J as for the objective and convention. C of theta hat given x theta is equal to theta minus theta hat squared p of theta given x d theta from negative infinity to infinity. Good. If you are not given a domain, we just put it negative infinity to infinity. Right, all theta. Okay, great. So this is step 1. Now step 2, let's simplify this. So this is step 1 and 2. This is only step 1, then step 1 and 2. So the steps are actually fairly intuitive here. Now we need to simplify this expression. You get theta squared plus theta hat squared minus 2 theta hat p of theta given x d theta. Okay, we are almost there now. Now the goal is to differentiate j respect to theta hat and set it to 0, right? Remember, we want to find the theta hat. So we differentiate that. Theta is a true value. So step 3, round of j, round of theta hat is equal to negative infinity, infinity. Theta square respect to theta hat is 0. This becomes 2 theta hat minus 2 theta p of theta given x d theta equal to 0. Therefore, what we want is that integral of negative infinity to infinity of theta hat p of theta given x should be equal to theta p of theta d theta. This also d theta. Good. Right? Almost there. Now, respect to the integration is respect to theta. This theta hat is constant respect to theta. You can take it out of the integration. You get theta hat negative infinity to infinity p of theta given x d theta negative infinity to infinity theta p of theta given x d theta. Look at this. What is this expression? Whether it's posterior or anything else, is a probability after all. You are calculating the probability for all value of theta. What is this? 1. Axiom of the probability. This is 1. Right? Therefore, is to use scalar theta hat is equal to negative infinity to infinity theta p of theta given x d theta. But what is this? Everyone, what is this one? What is this expression in a simple form? This expression is known as expected value of theta given x. Isn't this correct? This expression is known as expected value of theta given x. Right? Remember, how would you define the expected value of theta given x? This would be theta p of theta given x, d theta, exactly. So interpretation, you need to interpret what we found. Interpretation. The theta hat, the estimator, is equal to this, is equal to posterior mean. This is called posterior mean, right? Now, what is this expression? Look at this one. Remember, in the context of MMSE, I said after you observe random variable x, let me just note in MMSE, so they are all related together. So my goal is that to be able to give you enough information until you can connect all these dots together. In MMSE, the best estimator for random variable theta after observing random variable x is, what was that? Was expected value of theta x. Isn't that the same? They are the same. So MMSE, therefore MMSE is the class of Bayes estimator when the cost function C of t theta is equal to quadratic cost. Okay, so we could just start from the Bayes estimator. We could start from the Bayes estimator and we say, you know what? Now that you understand the Bayes estimator, go ahead and replace the C by the quadratic cost. Then you get MMSE. So what is MMSE? MMSE is a type of Bayesian estimator when the cost function is quadratic cost. Good. Easily. So now we relate this one to MMSE. We had a long lecture on MMSE, series of lectures on MMSE. Now everything is connected to each other. Case 2. Assume now C of t, C of theta, theta hat is equal to this absolute value. What if instead of the cost function that is quadratic, I have a cost function that is absolute value of theta minus theta? Okay. No worries. All we need to do, change the color. We are going to here. Okay, we write the definition. Integral from negative infinity, infinity, theta minus theta hat times posterior d theta. Just write a definition. That's all you need to write. Now we have a basic integration problem. The argument of the integral, remember, is d theta. Theta is what we are conditioning on. Therefore, if I have from negative infinity to theta hat, if this means that, so let me just write it here as a note. If this is, I will write the note here. I will write this minus this is equal to theta minus theta hat if theta is greater than theta hat, and theta minus theta hat marked by a negative sign if theta is less than theta hat. Good? Great. So now negative infinity to theta hat, this means that theta is less than theta hat of the negative theta minus theta hat p of theta given x d theta plus theta hat to infinity, theta hat to infinity, theta minus theta hat p of theta given x d theta. Good. So this note is only from here to here. It's not the rest of it is part of a solution to the problem. Now that we have these, let's go ahead and differentiate. Let's call this one J. Usually don't want to write this on this. Okay. Now round of J, round of theta hat is equal to the first argument, theta is nothing, negative theta hat is -1, but there is a negative outside, becomes 1, become p of theta given x d theta plus theta hat infinity. This time we don't have any negative outside, we have negative theta hat becomes negative p of theta given x d theta. This is equal to 0. Let's write one more step here just in case. So here what we have is negative infinity theta hat p of theta x d theta minus, just move the negative sign outside the integration, p of theta given x d theta 0. Okay, good. Great. So we have one equation here. This is one equation. I would call this one what equation? I would call this one equation 2. Okay, I will call this one equation 2. Great. Okay, now we know something very important here. We know that, look at this one, negative infinity to theta hat p of theta given x d theta plus theta hat to infinity p of theta given x d theta. We know this is equal to 1. I'm saying that we are integrating p of theta given x from negative infinity to infinity. This is equal to 1, right? So let's call this one equation 3. Good. Now look at equation 1 and equation 2 and 3. So if it's easier to look at that, let x to be negative infinity to theta hat. You don't have to do this. What if it's easier to look at that? And y, perhaps it would be better to name this one z, since we have already x. P of theta given x, theta hat to infinity d theta. So based on equation 2 and 3, we have z minus y is equal to 0 and z plus y is equal to 1. Add them up, you get z is equal to 1/2, y is equal to 1/2. Therefore, we know negative infinity to theta hat, p of theta given x, d theta is equal to theta hat, p of theta given x, d theta is equal to 1/2. Great, we get this expression. But what does it mean? The interpretation, after all, is the most important thing. So each color, we write the interpretation here. So up to now, we work out the math. Good. We know what we are doing exactly. We know the cost function. We know our math is correct, but what's the interpretation? So integral from negative infinity to theta hat of the posterior distribution is equal to integral from theta hat to infinity of the posterior distribution is equal to 1/2. This 1/2 is important. See, 1/2 is 1 divided by 2, right? So probability can be maximum 1. This 1/2 means it's exactly in the middle. Right, it's exactly in the middle. 1/2 from negative to theta hat. This is theta hat. From negative to theta hat, this is probability 1/2. From positive is probability is 1/2. Right. Therefore, theta hat is the median of posterior distribution. Great. Theta hat is the median of the posterior distribution. The theta hat, and given this cost function, which is the absolute error, they call this estimator. This estimator is known as least absolute error estimator, or LAE. See, if you have heard of LAE, this is what LAE is, right? So LAE, the best estimator under LAE is the median of posterior distribution. So we had a conditional mean of the posterior, or conditional posterior mean. Now we have a median of posterior distribution. Conditional mean happens when the estimator is quadratic cost. Now when the estimator is absolute value, we get the median of posterior distribution. See, these are all part of Bayesian estimation, all type of Bayes estimator. Good, great. Let's go for another case, case 3, which is kind of maybe the most important one. Case 3. What if the cost function, I want to use another color here. What if the cost function C of t theta hat is equal to this 1 and 0? As I said multiple times in my videos, then what if the cost function is like this? For absolute value of theta greater than theta hat, absolute value of theta is less than theta hat. Right? What if we have this cost function? But then what would be the best estimator? Let's go ahead and follow the same procedure. J is equal to expected value of C theta theta hat given x. So this is going to be from negative infinity, infinity C is 1 or 0. Let's just write it as it is. And we're going to write it. So under what case is 1? Let's have a note for ourselves here. It's 1 when theta is greater than theta hat, or when theta is less than negative theta hat. So from negative theta hat, from negative infinity to negative theta hat, p of theta given x d theta plus theta hat to positive infinity p of theta given x d theta. Right? Good. That's what we have. Make sure that everything is readable. So this is what we have. So let's have some sort of a diagram for ourselves. Let's have something like this. And this is theta hat. This is theta hat. Let's say this is negative theta hat, and this is theta hat. Let's make sure we know what we are doing exactly. From negative, and from positive. From negative infinity to negative theta hat is what we have here. From theta hat to positive infinity is what we have here. Right, so we expand these two areas. Right, but this is left. From theta hat to, from negative theta hat to theta hat. Okay, so J is equal to 1 minus integral from negative theta, just look at this diagram that I have here, look at this, to theta hat of posterior distribution d theta. Okay, good. J is equal to that. When you sum these two expression, when you sum these two, you get this J. Good. Now, we want to minimize J. So the goal, to remind you, the goal is to minimize J, which means we should maximize integral from negative theta hat p of theta given x d theta, right? So in a sense, we are looking for a maximum value of this. In a sense, the best theta hat is the maximum, the theta hat that maximizes this expression. Okay? So the best estimator, let's put it here, the best estimator, let me see where are we in the, for the equation, keeping 3, let's make this one 4. Therefore, the best estimator is the theta hat that maximizes the 4. Okay, let's make it a little bit more compact. Let's bring it here. Good. Okay, so what does it mean? We want the estimator that maximizes this expression. Therefore, the best theta hat, the best estimator for theta hat is the one that maximizes the posterior distribution. Or we are looking for the mode of the posterior distribution, They're all equivalent. This estimator, this well-known estimator, is known as MAP, maximum a posteriori probability. the one that maximizes the posterior distribution. During the map, remember, during the ML, the goal was to maximize the likelihood. During the map, the goal is to maximize the posterior distribution. Therefore, note, maybe this color, map is a special class of Bayes estimator when the cost function is 0, 1 cost or loss function. Okay, good. So we proved that map, MMSE, and this absolute error criterion, they are all a special class of Bayes estimator. Okay, good. So that's it for this video. Thank you so much for listening. Like always, if you like this content, please subscribe to my channel. Please also like and share the video with your friends, and see you all in the next video. Thank you so much.